Okay, so this is again the last talk in the session, and start with a note. So I work for Adobe Research and of the Bangalore campus, and so I just traveled yesterday, and so this is, I just realized when the whole schedule was being put together, this is one of the bad times to present the talk, particularly when you have almost 12 hours from your original home time zone. You're completely jet lagged. But let me just hold up and go through this talk. But having said that, so this talk is about I mean, it was initially we submitted that as an inspiration-driven experience transfer, but then one of the reviews, one of the common points across all the reviews was that the inspiration in this particular context was was a loaded one. So we wanted to make it more specific, and then we changed our title to an exemplar-driven or exemplar-based experience transfer. So in today's era, so both in computer vision and NLP, there is a lot of buzz around style transfer. So this is somewhere, inspired from those terminologies where, oftentimes you come across a lot of banners, in different forms, in hoardings, web ads, and in flyers, and any invitations that you get. And so the idea here is, for an experienced user, you see that you can immediately sort of figure out what is the underlying template and how can you bring up those designs into your own, for your own content and things like that. But think about a novice user who is not doing the design day in, day out, but they just want to sort of design their next birthday greetings or birthday invite for their kid or various other use cases. So in these cases, so you will want to essentially take some of these banners and put your own content on them, and so that brings into an interesting dilemma. So people often wish they see something and they can put in their own content out there, and so this problem was, essentially, that brings to the problem that we are trying to solve, wherein you have an exemplar and can you essentially transfer the experience of the exemplar image used for your own content. So more succinctly, the problem is given a set of content and an exemplar set of exemplar images, can we essentially transfer the content into the inspirational experience? And so what is the content here? Say the content is, you might have some messages that you might want to put in the experience, in the sort of the banner, and that is what we call as a content. And the exemplar images are sort of the example banners or example designs that you want to use. And the final output is something that can essentially use the design components and bring in and put your content into that banner. Well, so our larger objective here is, so when you have these exemplars, our system needs to have the capability to extract the underlying layouts and come up with what was, and make a decisioning on what the underlying template was, and use this layout extraction to come up with different combinations so that the final layout is achieved. Of course, this is far from being a final output. As you would see, there are, I'll touch upon what are the other aspects that are open, that are open to be solved in this whole extraction and the final optimization part. But this is roughly our larger objective. So our solution, so naturally we broke our solution into two parts. One that was sort of focused towards extracting the layout, and the other one that was focused towards using these extracted templates to come up with layout combinations. So I'll pause here and sort of touch upon what was the interesting thing. So, or what were our major contributions here. So if you just take, look at an image and sort of want to extract, say, what was the underlying constituent parts of the image, there are a lot of work in the computer vision literature that does that. And but they do it for images in the context of what was the object underneath and things like that, and they don't necessarily transfer naturally into the single page graphics and things like that, which was one of our primary contribution here, where we tried to adapt some of the techniques that are out there in the world of computer vision in the semantic segmentation and object recognitions for extracting layouts from a single page graphic design. And once you have these templates, then there are quite a lot of work in the world of single page graphic designs for the layout optimizations. But we have leveraged some of those work to, because once you put in the user content into a template, then the template itself, the original template might not hold due to the difference in the content and things like that. So we have leveraged some of the existing work towards optimizing the final look and feel of the layout. Now let me get into the details of each of these parts. So first, so the first step, as I said, so we have an exemplar, we have a sample banner from where we want to extract the underlying template pieces. So for that, we consider this banner as an image, and we try to identify what were the individual parts of the images. How can we essentially identify it at a pixel level? For that, we used data from corpus of design, which had their underlying metadata, from where we extracted what were the different classes. So in our class of images, we had an image, we had a text, and we had shapes as different components of the banners. And with that, we trained fully convolutional neural networks, which is again one of the the state-of-the-art technique for semantic segmentations of images. We leverage that in this case to come up with segmented banner. So what you see, suppose our input banner was something like this. So the algorithm identifies this the cyan part of as the image, which is color coded in blue here, and then the piece here is identified as a shape, which is color coded in red here, and then it identifies the parts of this banner that contains the text, which is color coded in green. Obviously, this cannot be used as is to to understand what the underlying template was, because this puts it at a puts it at a pixel level, and you can't necessarily have define elements and sort of add the contents into this part. So this required further processing, which is what we called as template extraction, where we take that take the segmented output from the fully convolutional neural networks, and we do a sort of a post-processing where we go in from every, from the image of the, from the segmented output, we essentially look at every pixel and we do a neighborhood search, and we try to come up with a bounding box that can essentially define that particular design, that particular element in the banner. So what this yields is sort of a template that constitutes different rectangular bounding boxes of say different components in the input banner image, say be it the images, shapes, or the text. Well, this was one way of solving it. Again, once we had this approach, then we wanted to explore, are there any other ways of looking at this problem and formulating this? Looks like we can, wherein because this was a two-stage process where we do a pixel-wise identification of what those pixels were and then processing it to identify what the templates were. An alternative is to just combine the two, which for which you can leverage you can potentially formulate that as an individual object detection problem, where we used mask RCNN to essentially combine the two steps and identify what are the different parts of this image that constitutes the layout. So ultimately, at the end of this step, what you get is in the input image, in the input banner that we have different parts of the templates that are identified, and their coordinates blocked, so that we have their height and width and where they start, and that sort of an information. So now in order to test this part, so we started with the ground truth banners, and we tried to extract the underlying template. So in these cases, we did have an information of what were the underlying designs, and we tried to recreate those templates with our algorithms. So we measured the performance in terms of the overall accuracies, in terms of at every element wise how much it matched with the ground truth, and also with the F1 score of the underlying classification task. So as it turns out, so if we just take the pure segmentation output from the fully convolutional neural networks, it was at a pixel level, it was perhaps performing better than the other two algorithms. But since the output of FCNN is as such cannot be used directly to extract the underlying template, the real comparison basis is between where we have the segmented output that was post-processed to extract those bounding boxes and thus the underlying templates. And we compare that against the object recognition, object detection like frameworks from mask RCNN. And while they were pretty comparable, but in certain places, as we could see, the FCNNs were sort of getting more precise than the mask RCNNs. So we proceeded with the FCNN-based framework. So to close, to summarize the first part, for the layout extraction, we have the input image, and from where we wanted to extract what were the underlying constituents of the images so that we could extract the underlying template. So we resorted to an image segmentation and an object detection sort of a frameworks. But we found that an FCNN-based semantic segmentation followed by local search to identify the bounding boxes were better. Now what we have, now we have the templates. Now we need to essentially put in the user content into this template and then sort of optimize that into a good layout. So this first we need to understand what good layouts are. For that what we did was we took a bunch of banners that was designed by the experts, and we took that we have started with an assumption that these were indeed definitions of an inherent definitions of how good banners should look like, and then we wanted to essentially figure out a way in which we can optimize our banners once they have the user content in, so that it can look it can have various aspects that these banners have. For that we needed different dimensions, so we again leveraged the work by O'Donovan to define different aspects of the goodness of this underlying design. So they considered a lot of factors like alignments and spread, and wherein alignment was around along the x directions or the y axis, and the spread was if they were sort of more spread out in the banners or something like that, and or if there was a better balance of these different components, and were there sufficient white spaces in the banners, in the single page graphics, and so on and so forth. So once you have defined these, the desirable characteristics that we want to evaluate on the banners, then we need to essentially figure out what is a good combination of these energies that can make that can give us a good score of how good is the particular layout. For that, we learn the layout energy functions we have a weighted sum of these energy functions and then we have a nonlinear inverse optimization algorithm that can essentially iterate with an initializations to find out what is a good weight. Again, so the weights indicate how each of these factors are here. This is just an example value. This is not the actual value that we finally got. But the idea here is these weights essentially indicate how much importance we give to those individual factors, and so on. And why this is important? Because in the next stage, we want to use this energy function to essentially optimize to fine-tune the final layouts that we have. So here, we use a simulated annealing-based approach where it essentially computes the energy of the banner in question, and it then tries to optimize it towards for getting it into a better energy state. So we achieve this by the use of proposals, wherein this is sort of the reason we have to go into this sort of an algorithm rather than a more convex or a more traditional optimization routine is that the energy functions that we have defined, it has different it has different aspects, and it doesn't have a sort of a single function that can optimize that or find the global minima. So we need to essentially resort to such a framework which has a trial and error sort of a technique. And therefore, so we have to define different proposals where it allows the larger algorithm to explore the whole space of good, whole space. So for that, we define various proposals that would optimize each of those dimensions of the energy functions. Like say we aligned two elements randomly, or we removed the overlaps between two elements, and we changed the positions of a particular element and things like that. And so the idea of these proposals is, so you have the the content in the banner, and now you just try to adjust different elements of those, of your banner now, so that it gets better and better in terms of the overall energy function that we had defined. So by this way, so once you have put in your own content and you optimize that, it gets it gets better on the different energy functions that we had designed. So for the final output banner, it can look something like this. And in order to evaluate this, we mixed, we had a mix of the designer generated and the machine generated banners, and we had a mechanical Turk survey where where the users were shown these set of banners in a random mix, and we asked the users to rate the different aspects of the banners on a 5-point scale. So, we were particularly interested in those aspects that the algorithm, the layout, that we were optimizing, the energy functions that we were particularly optimizing for. So, and the alignments, overlap, and the spread, which was our major components in the energy functions. And obviously, so the idea is not to beat a designer in terms of the performance, at least, but for a novice user, at least to give them a starting point so that they can get a good quality banner, like how someone, with of some similar quality. So in terms, in that aspect, so our larger, while the overall scores were not up to the designers, because obviously these were machine generated, but in terms of the individual aspects of these energy functions, we were indeed able to achieve what we were shooting for. So these were some of the examples of some machine generated banners, and so the primary takeaway is, we had here, our primary contributions is about extracting the templates of banners by using various frameworks. And once we have the extracted templates, once you put in the user's content, we have an approach that can essentially fine-tune the layout with the user's content. And the larger approach is potentially can be extended for multiple banners, where we can combine different, two banners, extract their elements, and mix and match for providing the final banner. But however, there are a lot of open problems out here. So over here, we just try to extract the templates and sort of mix them up. But we didn't really consider what was the visual saliency of these banners, which is which is again an interesting problem, and there could be a lot of there is a lot of work in this direction, at least in the computer vision side of the story. But we want to leverage some of them and use the font predictions and various other aspects, so that the final banners that we can essentially synthesize are more realistic and more complete as possible. So that's about it, and thank you.
All right, this is the last talk, so we can go a little bit later, but we have 1 or 2 minutes for questions, if someone has one. If not, I wanted to ask one really quick. I'm interested in the runtime of this. So just to make one banner, how long does it take, and which parts are the slowest?
So in our observations, I think it takes about a minute or minute and a half with normal computes.
Okay.
And I think so in terms of the initial segmentations, I think it is a prediction. It is an inferencing task. So that is sort of interestingly, that is not the computationally heavy part. It is rather the second part where you try to optimize that. While one might feel that that might be an overkill for the kind of problems, because oftentimes with the templates you get a more or less complete content. So it is just, if the energy, if your initialization is better, then that converges faster. But the real challenge comes when you want to sort of mix and match different templates. At that point, the second part of the algorithm, that is the layout combination part, gets a bit more computationally expensive.
So great, thanks. We have one question back here.
Thank you. Great talk. Blake Williford, Texas A&M University. Question was, did the people that used it, did they provide any feedback on, how they liked it, whether they liked it or not, or any qualitative data?
Was it again? Sorry?
Was like the qualitative, did you receive any qualitative data about kind of how pleased people were with the results and of the banners and so forth?
So, is your question about how, did we essentially have a qualitative feedback on how these banners were and in the look and feel and those sort of things? No, so our questions were so our objective was to mix and match the user-generated and the machine-generated banners, and we asked them questions around what is your score on the alignment of different elements in this banner and things like that. So that was, we limited it for different, just for a limited set of dimensions, because, the minute we go to, say, a mechanical Turk like framework, we cannot assume too much about their knowledge of design and things like, so therefore we limited our questions to some pointed aspects on the banners and just one on the overall, how did that look like.
Got you. And one other quick question is, do you think you could apply this methodology to other similar domains, for example websites and just nothing? So cool.
Yeah, so we did actually try those on the websites as well. So in the website case, I think the first part of the algorithm may or may not sort of hold, because the way we extract the layouts might be different. But the second part, if you just look at it from a purely sort of visual perspective, the second part is sort of generic enough and it can extend into that, and we have experimented on that one, although that does not include in the paper.
All right, thank you all for coming. Then I'll close the session. Let's thank our speakers.